Imagine yourself standing beneath a velvet sky. It is a night without clouds, without the distraction of city lights. Only the quiet rhythm of your own breath and the endless expanse of stars above you. You tilt your head back, and for a moment, the world beneath your feet disappears.
Yes.
The ground, the trees, the air, even the sense of time seems to fade, until there is only you, a fragile observer, staring into an ocean of light that stretches beyond imagination, and then the thought arises. The same thought that has haunted human minds for thousands of years. Does it end? When you look at the night sky, are you staring into an infinite abyss? A cosmos without boundary? A vastness that never stops? Or does there exist, somewhere far away, a wall, a curtain, a final edge beyond which there is nothing at all? This question is not just scientific. It is ancient. It is spiritual. It is deeply human. Because to ask whether space ends is to ask whether existence itself can be contained, whether reality is something finite like the surface of a planet, or whether it is an endless ocean that dwarfs all human comprehension. Long before the first telescope was built, before the first equation was drawn across parchment, humans gazed upward with the same awe. I'd imagine our earliest ancestors sitting by a fire in the open fields. The night would arrive, shadows would deepen, and then one by one the stars would reveal themselves. Pinpricks of silver light scattered across the darkness, each one whispering of mysteries beyond reach. To those first observers, the heavens were not empty. They were alive. Stars became gods. Planets became wandering spirits. The sky was a dome, a protective ceiling built by some unseen hand. And still, even then, someone must have asked the question, what lies beyond the dome? If I could climb past the stars, where would I arrive? In Mesopotamia, scribes recorded tales of layered heavens stacked one above another, a cosmic architecture where gods moved unseen. In ancient Egypt, the night sky was imagined as the body of a goddess arching over the world, her skin decorated with shining stars. In Greece, philosophers debated whether the universe was finite, bounded by crystalline spheres, or whether it stretched forever without limit. Again and again, across cultures, across centuries, the same curiosity emerged. Does the cosmos end, or is it endless? The human mind, remarkable though it is, struggles with infinity. Try to picture it. Endless distance, endless stars, endless space. No walls, no borders, no edges, just forever. Your thoughts attempt to reach outward, but eventually they recoil, collapsing back into the safety of the finite. It is easier to imagine a wall, an edge, something physical that marks the end. It is easier to draw a circle around the universe and say, here, this is all there is. Beyond this line, there is nothing. But nothing is not easy either. What is nothing? A void? Blankness? And if nothing truly exists beyond the edge, then doesn't that nothing become a kind of space itself? The mind spins, caught in paradox, and the mystery deepens. This is why the question, does space end, has survived across centuries. It is not merely scientific. It touches something deeper, the limits of thought itself. Over time, myths gave way to philosophy, and philosophy gave way to science. In the hands of thinkers like Aristotle, Ptolemy, and later Copernicus and Galileo, the heavens were no longer only divine symbols, but physical realms governed by rules that might be understood. Yet even science could not escape the question of boundaries. Aristotle believed the universe was finite, wrapped in a great celestial sphere. For him, the cosmos was contained, ordered, and eternal. Centuries later, with the rise of Newtonian physics, the universe seemed infinite, stretching without end in every direction. Each age, each generation, has inherited the same puzzle. And every time we push the boundary of knowledge farther outward, the horizon seems to retreat. Today we possess tools our ancestors could never have imagined. Radio telescopes, space probes, satellites, deep field images from observatories that capture galaxies billions of light years away. We can measure cosmic microwave background radiation, map dark matter, and calculate the expansion of space itself. And still, after all of this, the question lingers. Does it end? Astronomers tell us that the observable universe is 93 billion light-years across, filled with trillions of galaxies. And yet the word observable is crucial here. We can only see as far as light has had time to travel since the birth of the universe. Beyond that, we do not know. The edge of our sight is not the edge of space itself. It is simply the edge of what light has revealed. Beyond it could be more galaxies, more stars, more endlessness, or perhaps something entirely different. Notice something extraordinary. The same question that lived in the hearts of our ancestors lives within us still. The campfire has been replaced by digital screens. The myths have been replaced by equations. The stories of gods and domes have been replaced by cosmic background radiation and quantum theory. But at the center, at the deepest point, we are asking the same thing. Does existence have a boundary? Does reality itself end? There is something profoundly humbling in that continuity. We are not so different from those who stood under ancient skies. We inherit not only their DNA but also their wonder. So tonight, as you look upward, try to hold both truths in your mind, that you are a modern being, armed with the knowledge of galaxies, physics, and cosmology, and also an ancient dreamer, staring into the unknown, asking the same unanswerable question. Does space end, or is it endless? A question without boundary, echoing through every generation. And if it does not end, if it stretches forever, then perhaps the mystery is not only out there, in the sky above, but within us, in our endless need to seek. When humans first began to ask whether the universe ends, they did not possess telescopes, equations, or satellites. They had only their eyes, their imagination, and the stories they carried through generations. Infinity for them was not a mathematical symbol. It was an idea that shimmered in the night sky, a mystery wrapped in mythology, philosophy, and faith. To trace the human view of infinity is to trace the evolution of thought itself, from whispered myths around fires, to carved symbols on temple walls, to the manuscripts of philosophers, and finally to the careful measurements of early astronomers. It is a journey that spans thousands of years across continents and cultures, all bound together by the same question. Is there an end to existence, or does it stretch on forever? In the heart of ancient Greece, thinkers wrestled with infinity as if it were a living thing. To them, the universe was not just a backdrop for human life. It was the stage upon which meaning itself unfolded. Aristotle, perhaps the most influential of them all, could not accept the idea of an actual infinite cosmos. He believed infinity existed only in potential, never in reality. For example, you could always divide a line into smaller and smaller parts, but you would never reach the end of those divisions. Infinity, for Aristotle, was a process, not a thing. In his vision, the universe was finite. The Earth sat unmoving at the center, and around it, crystalline spheres carried the planets and stars. Beyond the outermost sphere lay the prime mover, a divine principle that set the cosmos in motion. For Aristotle, there was no endless abyss. The heavens were contained, ordered, perfect. But not all Greeks agreed. The philosopher Anaximander spoke of the apeiron, the boundless, the infinite. To him, reality emerged from something without limit, something eternal and unending. His vision was radical. The cosmos itself might not be bounded at all. Here we see the tension that still lives in us today. The comfort of a finite cosmos, ordered and comprehensible, versus the terrifying beauty of an infinite one. Far from Greece, in the Indian subcontinent, thinkers were weaving a very different tapestry of infinity. In Hindu cosmology, the universe was not linear, but cyclical. Time itself was infinite, flowing in vast cosmic cycles called kalpas. Each kalpa spanned billions of years, a breath of the god Brahma. The universe would emerge, flourish, decline, and dissolve, only to be reborn again, endlessly, without beginning or end. The Vedic and Puranic traditions described multiple universes existing side by side, countless realms stacked beyond comprehension. The night sky was not a finite dome, nor was it a simple infinity of stars. It was an infinite dance of creation and destruction, an eternal rhythm where even gods were subject to the flow of time. What is astonishing here is the scale. Long before modern science spoke of billions of years, Hindu cosmology imagined cosmic cycles stretching across unimaginable spans of time. Infinity was not abstract. It was the very structure of reality. As the light of Greek philosophy passed into the hands of the Islamic Golden Age, scholars in Baghdad, Damascus, and began to refine and expand humanity's understanding of the cosmos. Figures like Al-Farabi, Ibn Sina, Avicenna, and later al-Biruni and Ibn al-Haytham carried forward the Greek traditions while also questioning them. They built observatories, mapped the movements of the stars, and developed new mathematical techniques to measure the heavens. For many Islamic philosophers, the universe was vast, but finite, created by God with order and harmony. Yet within Islamic mysticism, infinity was often embraced as a reflection of the divine itself. The endless heavens became symbols of God's boundless nature. Looking into the night sky was not only an act of science, but also of devotion, a way to glimpse infinity through creation. Al-Biruni, in particular, speculated on the vastness of the universe and the possibility that the stars extended far beyond what could ever be observed. In his writings, we see a merging of scientific precision and spiritual openness, the acknowledgement that the cosmos might be larger, stranger, and more infinite than Aristotle's ordered spheres ever allowed. Across cultures, myths filled the gaps where science could not reach. The Babylonians imagined a universe resting on great waters, with the heavens above as a vast, endless ocean. The Norse spoke of Yggdrasil, the world tree, connecting infinite realms. The Chinese told of cosmic eggs from which worlds emerged, floating in a boundless expanse. Even in Mesoamerica, the Maya conceived of layered heavens and underworlds, stacked infinitely upward and downward, mirroring the cycles of the stars. These myths, though different in detail, share a common theme. When humans looked at the night sky, they saw something that defied limits. Whether through gods, trees, or cycles, they expressed infinity in symbols and stories, reaching for something their minds could feel but not fully grasp. By the Middle Ages and Renaissance, the seeds of modern science began to stir. Thinkers like Giordano Bruno dared to imagine an infinite universe filled with endless worlds, each with its own suns, and perhaps even its own life. For this he was condemned, for infinity threatened the very order that religious and philosophical systems tried to preserve. Yet his vision planted a seed. Perhaps infinity was not just a myth, not just a philosophy, but a physical reality. Perhaps the stars in the sky were not ornaments on a sphere, but suns scattered across an endless cosmos. These early scientific attempts did not yet have the tools of telescopes powerful enough to see galaxies, nor the mathematics of relativity or quantum mechanics. But they carried the torch of imagination, daring to break the cage of finite heavens and step into the idea of a boundless universe. Across Greece, India, the Islamic world, and Europe, infinity was not only about the stars, it was also about us. Infinity reflected the human struggle with limits, the limit of life, of knowledge, of imagination. To speak of endless space was to speak of endless possibility, but also endless mystery. When ancient poets wrote of skies without end, when philosophers debated the nature of the boundless, when astronomers mapped stars beyond stars, they were not only describing the cosmos, they were describing the human mind, forever pushing against boundaries, forever reaching for what lies just beyond. And so, the human view of infinity is a tapestry woven from myth and mathematics, philosophy and devotion, science and imagination. From Aristotle's finite spheres to Anaximander's Epiron, from the Hindu cycles of endless time to the Islamic astronomers' expanding heavens, from Bruno's daring vision of infinite worlds to the myths of boundless skies, all of them echo the same wonder. The universe may end, or it may not. But our fascination with infinity reveals something just as important, that to be human is to question limits, to feel the weight of mystery, and to gaze upward with the unshakable belief that beyond the stars lies something more. As we leave behind the myths and step into the age of science, the question will only grow louder. Because if infinity is not just an idea but a reality, then how can we, finite creatures, ever hope to understand it? Empty space like ships across an ocean. We are speaking of the ocean itself growing larger. Space, the very fabric of reality, is stretching. That Stefri that space is not fixed but dynamic is one of the greatest revolutions in human thought. But this realization did not come easily. It took centuries of questioning, decades of observation, and the boldness of a few visionaries to dismantle the comforting idea of a static eternal universe. What they uncovered instead was a cosmos that had a beginning, is in constant motion, and might never end. At the dawn of the 20th century, Albert Einstein reshaped physics with his theory of general relativity. Published in 1915, it revealed that gravity was not a mysterious force pulling objects together, but the warping of space and time itself. Mass bends space, and curved space tells mass how to move. This elegant idea transformed the way scientists thought about the universe. No longer was space an empty, passive stage on which matter played out its drama. Space itself was part of the play, bending and shifting with every star, planet, and galaxy. When Einstein applied his equations to the cosmos as a whole, he stumbled upon a startling result. The universe should not be static. According to the math, it must either be expanding or contracting. But Einstein, like almost everyone else at the time, assumed the universe was eternal and unchanging. To fix the problem, he added something called the cosmological constant, a kind of anti-gravity term that kept the universe balanced in place. Later, he would call this the biggest blunder of his life. Why? Because the universe was not static at all. In the 1920s, an American astronomer named Edwin Hubble was peering through the giant telescope at Mount Wilson Observatory in California. He studied distant galaxies, fuzzy smudges of light that until then were thought to be clouds within our own Milky Way. What Hubble discovered changed everything. First, he proved that these smudges were not part of our galaxy, but galaxies in their own right, vast star cities millions of light years away. The universe, it seemed, was much larger than anyone had imagined. But then came the truly shocking revelation. As Hubble measured the light from these galaxies, he noticed something strange. The light was redshifted. Just as the sound of a train whistle drops in pitch as it moves away, light stretches to longer, redder wavelengths when its source is moving away. This meant that the galaxies were not standing still. They were receding from us. And the farther away a galaxy was, the faster it seemed to move. This relationship, now called Hubble's law, revealed that space itself was expanding. The galaxies were not flying through space. Space was carrying them apart. Hubble's discovery shook the foundations of science and philosophy alike. If the universe was expanding, then in the past it must have been smaller. Trace the expansion backward, and you arrive at a moment when everything was compressed into a single, unimaginably dense point. This idea became known as the Big Bang Theory. Far from a quiet, eternal cosmos, the universe had a dramatic origin some 13.8 billion years ago. From a state of incredible heat and density, space itself burst into existence, carrying matter, energy, and time along with it. The Big Bang was not an explosion in space. It was the expansion of space. There was no outside for it to explode into. Space and time themselves began in that moment, and have been stretching ever since. At first, many resisted the idea. Einstein himself was skeptical, preferring the comfort of a static universe. Some scientists argued for an alternative steady-state model, where new matter continually appeared as the universe expanded, keeping its density the same. But over time, the evidence piled up: the cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of galaxies, all pointed to a universe born in a fiery beginning. The Big Bang was not just a scientific theory. It was a philosophical earthquake. It told humanity that the universe had an age, a history, and perhaps even an end. But if the universe is expanding, how far can we actually see? This question gives rise to the concept of the observable universe. The spherical region of space centered on us, defined not by what exists, but by what light has had time to reach us. Light travels at a finite speed, about 300,000 kilometers per second. As vast as this is, it is not infinite. When we look at the stars, we are looking into the past. The sun, as it was 8 minutes ago. The nearest galaxy as it was 2.5 million years ago. Since the universe is 13.8 billion years old, you might think we can only see 13.8 billion light years in any direction. But because space itself has expanded during that time, the true radius of the observable universe is about 46 billion light years. Beyond that lies more universe, but it is forever hidden from us, its light unable to bridge the growing gulf. This observable horizon is not the edge of space itself, it is the edge of our vision. The universe likely stretches far beyond what we can see, perhaps infinitely. But for us, confined by the speed of light and the age of the cosmos, the observable universe is all we can directly know. If the universe is expanding, what does that mean for galaxies, stars, and us? On small scales, within galaxies, or within clusters of galaxies, gravity holds things together. The Milky Way is not expanding, neither is our solar system. But on the grand cosmic scale, space is stretching everywhere, pulling galaxies apart like raisins embedded in rising dough. The farther away a galaxy is, the faster it recedes. Nearby galaxies drift away slowly, while distant galaxies flee at incredible speeds. Some are already receding faster than light itself, not because they are breaking cosmic speed limits, but because the space between us and them is expanding faster than light can cross it. This means that whole regions of the universe are slipping beyond our reach forever. Galaxies that we see today, faint smudges at the edge of detectability, may one day vanish from sight as the expansion carries them beyond our cosmic horizon. We are left with a profound truth. The night sky we see is temporary. The visible universe is shrinking around us, not in size but in what we can access. The stars will remain, but the deep universe, those distant galaxies glowing like embers in the dark, will slowly fade away. The story of space expansion is a story of perspective. Einstein gave us the equations, Hubble gave us the evidence, and the Big Bang gave us a beginning. The observable universe defined our limits, and the stretching of galaxies reminded us of our fleeting window onto the cosmos. Together, these discoveries shattered the dream of a static, eternal universe and replaced it with something far more dynamic, a universe in motion, alive with growth, and perhaps destined for endings we can scarcely imagine. Infinity was no longer just a myth or philosophy. It was now written into the mathematics of reality itself. And yet with each answer came new questions. If the universe is expanding, what is it expanding into? Does the expansion ever stop? Could it reverse? Or will it carry on forever, tearing the cosmos apart? These questions lead us onward, deeper into the mystery, to the edge of the observable universe and beyond. When you gaze up at the night sky, you might imagine that your eyes are opening a window onto infinity. But in truth, what you see, even with the most powerful telescopes, is only a small bubble, a cosmic horizon beyond which light can never reach you. This is not because the universe stops there. It's because the laws of physics and the nature of time itself set boundaries on our vision. In this section, we journey to that edge. We will explore what lies within our observable universe, what lies beyond in the unobservable universe, and how the faint glow of the cosmic microwave background provides us with the oldest image of reality. We will then ask, with all our technology, how far can telescopes truly see? And what happens when we peer beyond the limit of sight? Imagine yourself standing in the middle of a vast forest, holding a lantern. The light spreads out in all directions, illuminating a sphere of trees around you. Beyond a certain distance, your lantern cannot reach, and the forest remains dark. Our universe works in much the same way. Instead of a lantern, it is the finite speed of light that sets the boundary. Light travels at 300,000 kilometers per second, unimaginably fast but not infinite. Since the universe has existed for only about 13.8 billion years, the farthest light that can possibly reach us comes from a distance defined by time itself. You might think this distance would be 13.8 billion light-years, since that is how long light has been traveling. But because the universe has been expanding all the while, the true boundary is much farther away. The current radius of the observable universe is about 46 billion light-years in every direction. That means we can see a sphere of galaxies nearly 92 billion light-years across. But here's the catch. Beyond that horizon, the universe almost certainly continues, perhaps infinitely. Galaxies may stretch on forever or curve back upon themselves, but we will never know. No signal, no photon can cross the ever-expanding gulf to reach us. This leads to the chilling realization that much of reality is already and always will be unobservable. There may be countless galaxies beyond our reach, teeming with stars, planets, and perhaps even life, but they exist forever outside the curtain of our horizon. If the observable universe is our bubble of vision, what fills it? What is the farthest thing we can actually see? The answer is not a galaxy or a star or even a cloud of gas. The farthest thing we can see is light itself, the cosmic microwave background, CMB. To understand it, we must travel back almost 13.8 billion years, to the moment of the Big Bang. In the first moments of the universe, the cosmos was unimaginably hot and dense, a seething plasma of particles and radiation. Photons, the particles of light, could not travel freely. They bounced endlessly between charged particles trapped in a cosmic fog. But after about 380,000 years, something remarkable happened. The universe cooled enough for protons and electrons to combine into neutral atoms. Suddenly, photons were free to travel. The fog lifted. Light could move in straight lines for the first time. That ancient light still travels through the cosmos today. But as the universe expanded, the light stretched, cooling from blazing heat into faint microwaves. Today, it bathes the universe in a nearly uniform glow, detectable in every direction. This glow is the cosmic microwave background, and it is the farthest surface we can observe, the first visible wall of the cosmos. When scientists first discovered the CMB in 1965, it was like hearing an echo from creation itself. It provided irrefutable evidence for the Big Bang, showing us that the universe really did begin in a hot, dense state. When you see an image of the CMB, a modeled map of faint temperature fluctuations across the sky, you are looking at the earliest picture of the universe, a snapshot of the cosmos, when it was just 380,000 years old. Everything before that, the first moments, the inflationary era, the very birth of time, lies hidden behind this ancient curtain. With telescopes, we reach deeper into space, and therefore deeper into time. The James Webb Space Telescope, JWST, launched in 2021, can peer back over 13 billion years, capturing galaxies that formed only a few 100 million years after the Big Bang. The Hubble Space Telescope. Before it revealed galaxies so faint that they appeared as whispers of light at the edge of visibility. But no telescope, no matter how advanced, can see past the cosmic microwave background. That is the ultimate wall of vision. Beyond it, photons are trapped in the fog of the early universe. We cannot see into that era with light. Instead, scientists look for other messengers, neutrinos, gravitational waves, or imprints left on the CMB itself. These signals might allow us to probe the first instant of creation before light itself was free. So while telescopes can stretch our cosmic gaze almost to the dawn of time, they face an unbreakable limit. The observable universe is not only a question of distance, but of physics itself. An important realization is that our cosmic horizon is not fixed. With every passing second, light from more distant regions reaches us. The observable universe grows. Today, it is 46 billion light-years in radius. Tomorrow, it will be slightly more. But at the same time, the accelerating expansion of the universe means that many galaxies are receding faster than light. They may be visible to us now, but one day their light will no longer reach us. Slowly, the deep universe will fade away, leaving only our local group of galaxies bound together. We live then at a unique moment in cosmic history. A moment when the universe is young enough that vast horizons are still visible, yet old enough that telescopes can probe nearly to its beginning. In the far future, those horizons will shrink, and the night sky will grow empty. The concept of cosmic horizons is one of the most humbling truths of modern science. The universe is vast, perhaps infinite, but our vision is bounded. We are like sailors on a dark ocean, with lanterns that can only illuminate a bubble around us. Beyond that horizon lies mystery. Galaxies unseen, worlds unknown, perhaps even whole realms of physics yet undiscovered. The cosmic microwave background gives us a final snapshot, the first image of the universe's face. Our telescopes extend our eyes to the edge of time, but no further. Beyond that horizon, imagination must take over where observation fails. And so the question remains, if this is the edge of what we can see, Is it also the edge of what truly exists? Or does the universe continue endlessly, forever beyond our reach? These questions draw us toward the greatest cosmic mystery of all, the possibility of multiple universes, the multiverse, and the idea that our horizon is not the end, but just one bubble among many. You have a ship, not an ordinary ship, but one designed to never fail, to travel endlessly into the dark. Its engines hum with infinite power, its hull defies decay, and you, the traveler, are unaging. With curiosity as your compass, you set a single course, forward, forever. What would happen? Where would you go? Would you ever reach the end of space? Or would the journey itself reveal truths too strange for us to fully grasp? This thought experiment, while whimsical, is actually one of the most profound questions science can ask. To explore it, we must sail through the strange seas of relativity, cosmic expansion, black holes, wormholes, and the very structure of space-time itself. At first glance, the question seems simple. If you just keep going straight, surely you must reach an edge, a border, some sort of wall at the universe's end. After all, every map has edges. Every ocean has shores. But space is not like the oceans of Earth. It is not laid out on a flat surface with borders we can sail past. Instead, it is woven into the very fabric of reality, curved by gravity and stretched by expansion. Traveling forever doesn't mean moving through a container. It means moving along with the universe itself. And there's the first complication. You can't outrun the speed of light. No matter how powerful your engines, no matter how much fuel you burn, light remains the universal speed limit. Even if you travel at 99.999% the speed of light, you can never surpass it. The physics of relativity forbids it. So your infinite journey is already constrained. You can only move outward at the pace the laws of physics allow. As your ship races outward, distances are not measured in kilometers or miles. They are measured in light years. The distance light travels in 1 year, about 9.46 trillion kilometers. At first, the numbers feel manageable. In just 4 years, you could reach Alpha Centauri, the closest star system. In a few thousand years, you could cross the width of our Milky Way galaxy. But then the distances grow monstrous. The next nearest major galaxy, Andromeda, lies 2.5 million light-years away. Even at light speed, your journey would take longer than the entire history of humanity. Push further still, and you enter the cosmic wilderness. Billions of light-years between clusters of galaxies. To travel forever is to accept that distances will grow faster than you can cross them, as the universe itself stretches beneath you. Here's where Einstein's relativity offers you an escape hatch. As you approach the speed of light, time itself slows for you. To an outside observer, your journey may take millions, even billions of years. But for you, on board your timeless ship, the trip might feel brief. Hours could slip into centuries, centuries into eons. This means that in theory, you could live to see the farthest reaches of the observable universe. Not because you've cheated physics, but because physics itself bends perception. Still, relativity has a cruel catch. While time slows for you, the universe around you races forward. Galaxies age, stars die, black holes grow. You may cross billions of light years. But when you glance back, the universe you left behind is ancient, perhaps already gone. Now imagine your endless voyage takes you near one of the great cosmic abysses, a black hole. From afar, it might appear harmless, just another dark sphere among the stars. But get too close, and you cross the event horizon, the ultimate point of no return. Space-time curves inward, and all paths lead down. Not even light can escape. If you were reckless enough to plunge in, your forever journey would end abruptly. To an outside observer, you would appear frozen at the edge, stretched thin across the horizon. But from your own perspective, you would fall inward, in seconds, toward the singularity, the unknowable heart, where physics itself breaks down. Black holes are not edges of the universe, but they are edges of knowability. Boundaries where even the best equations stop working. If you seek infinity, they are deadly traps. But what if instead of a black hole, you found a wormhole? The equations of general relativity allow for such tunnels, bridges that connect distant regions of space-time. In theory, entering one could let you skip across billions of light years in an instant. It would be the ultimate traveler's dream, a shortcut across forever. The problem is wormholes may be unstable. They could collapse before you pass through. Some scientists suggest they would require exotic matter, negative energy, to remain open. If such things exist, wormholes could provide an actual escape from the limits of space. If not, they remain mathematical fantasies, beautiful but unreachable. Still, their possibility adds a whisper of hope. Maybe infinity can be tricked. Suppose you avoid black holes and wormholes. Suppose your ship flies clean through intergalactic space. You're still faced with the greatest barrier of all, the expansion of the universe. Space itself is stretching, and galaxies are being carried away faster than light. Even if you fly forever, you can never reach them. They recede faster than you can chase. This creates a sobering reality. The farther you go, the more the universe outruns you. Even with infinite time, your journey is confined to an ever-shrinking island of galaxies. Beyond that, infinity slips through your fingers, carried away on the current of cosmic expansion. So if you've traveled forever, would you ever hit a wall? A cosmic boundary? Most scientists believe the answer is no. Space does not appear to have an edge like the rim of a bowl. Instead, it may curve back on itself like the surface of a sphere. In such a universe, traveling in one direction forever might eventually bring you back to where you started. Not because you hit an edge, but because space loops. Alternatively, if the universe is infinite, you could travel outward forever and never repeat, never return, never reach a border. Forever means forever. But the cruel truth is this: because of cosmic expansion, you can never test it. The galaxies that might reveal the universe's shape are vanishing beyond reach. The edge, if it exists, hides not at a distance, but behind the horizon of physics itself. So what if you traveled forever? You would find marvels and mysteries. Black holes, wormholes, galaxies fading into the dark. You would experience time itself bending, the universe aging around you, horizons slipping away faster than you can chase. But you would never find an end. Instead, you would discover a deeper truth. The journey itself is endless, because the universe is either boundless or bounded in ways our senses cannot grasp. In this sense, to travel forever is not to reach a destination, but to participate in an eternal unfolding. You would become a witness to infinity, a sailor on a sea with no shore, where the horizon always retreats as you advance. And perhaps that is the point. The question of whether space ends is less about what lies ahead, more about how the very act of moving forward reveals the strange, humbling structure of reality itself. We began with a simple mystery. Does space end? We have traveled outward in thought experiments, explored horizons, even wondered if traveling forever could bring us to an edge. But now, an even bigger question rises from the shadows. What if our universe is not alone? What if everything we see, galaxies, stars, planets, and all of cosmic history, is just one bubble in a much larger sea of existence? This idea is not fantasy. It is called the multiverse. And though it sounds like science fiction, serious physicists debate it. Some even believe it may be the best explanation for why our universe looks the way it does. But is the multiverse real, or is it just a reflection of our endless human desire to imagine what lies beyond? The idea of multiple universes is not new. Ancient myths and philosophies hinted at parallel worlds long before modern science. Hindu cosmology speaks of infinite cycles of creation and destruction, countless universes born and dying like bubbles in an endless ocean. Medieval Islamic thinkers pondered whether Allah might sustain other worlds beyond our own. Fast forward to today, and the concept has resurfaced. Not in temples or myths, but in the equations of modern physics. Strangely, when scientists try to answer why our universe exists as it does, the multiverse keeps sneaking into the conversation. Let's start with one of the strangest possibilities: parallel universes. In quantum mechanics, the behavior of particles is unpredictable. Instead of fixed outcomes, physics gives us probabilities. When you flip a quantum coin, so to speak, the universe doesn't pick heads or tails. It holds both possibilities. One radical interpretation, called the many worlds hypothesis, suggests that every quantum decision splits reality. In one universe, you turn left. In another, you turn right. In one, you become a traveler of the stars. In another, you never leave home. This means there may be an endless branching of universes, each containing slightly different versions of you, living out every possibility. Now pause and consider the scale. If this interpretation is correct, then the multiverse is not a vast collection of galaxies. It is a vast collection of realities, each as real as our own. But here's the challenge. If every possibility exists, how can we ever test it? Is many-world science or just philosophy dressed in physics? Parallel universes are not the only path to the multiverse. Another contender comes from the ambitious attempt to unify physics itself, string theory. String theory imagines that at the deepest level, particles are not tiny points but vibrating strings of energy. The vibrations of these strings give rise to the particles and forces we see in the universe. But for the mathematics to work, string theory requires more than the 3 dimensions of space we know. It requires 10 or even 11 dimensions. What does that mean? It means that our universe might be just a 3D surface floating in a higher dimensional space. Imagine a soap bubble floating on water. To a tiny creature living inside that bubble, the bubble might feel like the entire universe. But from outside, we see that it's just one bubble among many, all jostling, all real. This leads to the idea of a brain multiverse, where multiple bubble universes, or brains, drift in higher dimensional space. Sometimes, they may even collide. Some physicists have suggested that the Big Bang itself might have been the result of such a collision. Think about that. Our universe might not have begun from nothing, but from the crash of 2 higher dimensional realities. And then there is the most famous multiverse idea of all, eternal inflation. In the earliest moments after the Big Bang, physicists believe the universe underwent a phase of rapid inflation, an unimaginable expansion faster than the speed of light. This inflation eventually slowed, leaving behind the universe we see.
Oh.
But what if inflation never fully stopped? What if it continues in other regions of reality, endlessly creating new universes like bubbles in a cosmic foam? In this picture, our universe is just one bubble. Beyond our horizon, other bubbles are inflating, growing, colliding forever. Some bubbles may have different laws of physics. Some may contain no galaxies at all, while others might teem with stars and life. It is not just poetic imagination. The math of inflation naturally predicts this bubbling multiverse, which means, in some sense, the multiverse is not a wild speculation, but the natural consequence of our best cosmological theories. But here lies the problem. If other universes exist, how do we see them? By definition, they are outside our cosmic horizon. No telescope, no spacecraft, not even light itself can bring us news of them. Some scientists argue that this makes the multiverse unscientific, since science demands testable predictions. Others counter that, while we may not observe other universes directly, we may see indirect clues, scars in the cosmic microwave background, or subtle imprints of bubble collisions in the earliest radiation of our universe. Still, the evidence remains thin. The multiverse is a stage filled with possibilities, but few testable scripts. Yet even without hard proof, the idea of the multiverse changes everything. If there are infinite universes, then every possible version of reality exists somewhere. Every dream you've had, every decision you did not make, every path untaken, all of them are played out in some alternate world. It raises profound questions. Are we unique, or just one of countless copies? Does meaning survive in a reality where everything possible is inevitable? And what does this say about our search for an edge of space, if our universe itself is just one bubble in an infinite sea? In some sense, the multiverse shifts the question of endings. It suggests that our universe does not end, because universes themselves may be endless. So where does that leave us? The multiverse is at once thrilling and frustrating. It could explain the deepest mysteries of physics. Why the constants of nature are fine-tuned for life. Why the Big Bang happened. Why our universe looks the way it does. But it may also remain forever beyond our reach, an eternal speculation. What we can say is this: whether or not the multiverse is real, the very fact that we can imagine it shows the power of human curiosity. Our minds refuse to accept boundaries. If the universe gives us an edge, we ask what lies beyond. If it gives us infinity, we ask what lies outside that infinity. The multiverse debate is not just about physics. It is about the human hunger for the unknown, the refusal to stop at the horizon. the endless question, what if? And perhaps in that way, the multiverse is already real, not as a physical fact, but as a mirror of our deepest longing to understand existence. When we ask, does space end? We're not only asking a question about the physical universe, we're also asking about the very nature of infinity. Infinity is not like any other number. You can't hold it, you can't write it fully, you can't even imagine it completely. And yet, infinity shows up everywhere. In philosophy, in religion, in mathematics, and in the very equations of physics. Tonight, let us step into the strange world where math tries to wrestle with infinity, and where infinity wrestles back. For diving into paradoxes, we must separate two different infinities. Mathematical infinity, abstract, exact, unchanging. A symbol written as infinity, treated with rules and logic. Physical infinity, the possibility that the universe itself is infinite in size, or in time, or in possibilities. The first infinity lives in our minds. The second might live in the cosmos. In mathematics, infinity is precise. For example, the set of all natural numbers, 1, 2, 3, is infinite. The set of real numbers between 0 and 1 is also infinite, but in a deeper way, containing an uncountable infinity of decimals. In physics, infinity is dangerous. Equations that produce infinity often signal that our theories are broken. For example, when Einstein's equations are pushed into the heart of a black hole, space-time curves infinitely, and we call it a singularity. Mathematics embraces infinity. Physics fears it. The German mathematician David Hilbert created a thought experiment to show how strange infinity really is. Imagine a hotel with an infinite number of rooms. Every room is occupied. You might think the hotel is full. But wait. A new guest arrives. Can they stay? Yes. The manager simply moves the guest in room 1 to room 2, room 2 to room 3, and so on forever. Room 1 is now empty. The infinite hotel is full, yet it can always accept more guests. Now imagine an infinite bus arrives, carrying an infinite number of new guests. Still, the hotel can make room by shifting everyone to even-numbered rooms, leaving the odd-numbered rooms empty for the newcomers. Hilbert's hotel shows that infinity doesn't follow ordinary logic. It bends our intuition. And yet this is the kind of infinity we may face when we ask about the size of space itself. If the universe is infinite, it is not just big. It is Hilbert's hotel big, forever stretching, forever welcoming more galaxies, more possibilities. Long before Hilbert, the Greek philosopher Zeno of Elea puzzled over infinity in motion. One of his most famous paradoxes is called Achilles and the tortoise. Imagine Achilles racing a tortoise who has a head start. Zeno argued that Achilles can never catch the tortoise. Why? Because to catch up, Achilles must first reach the tortoise's starting point. But by then, the tortoise has moved ahead. Then Achilles must reach that new point, but the tortoise has moved again, and so on, forever. The chase can be divided into an infinite number of steps, so how can Achilles ever finish? Today, mathematics answers with the concept of limits. An infinite number of steps can still add up to a finite distance. Achilles does catch the tortoise. But Zeno's paradox forces us to see that infinity hides inside even the simplest motions. Every time you walk across a room, you are performing an infinite sequence of smaller and smaller steps, whether you realize it or not. Infinity is not just one thing. Mathematicians like Georg Cantor revealed that there are different sizes of infinity. For example, the infinity of whole numbers. 1, 2, 3. It's called a countable infinity. The infinity of real numbers, all the decimals between 0 and 1, is larger, uncountable. Cantor proved something shocking. No matter how high you climb through infinities, there is always a bigger one beyond. Infinity is not a single wall, but a ladder that never ends. This raises a haunting parallel with the universe. If space is infinite, is it like the infinity of whole numbers? A repeating, countable pattern of galaxies? Or is it like the infinity of real numbers, so vast that every possible arrangement of atoms, every possible story, happens somewhere, sometime? When physicists model the cosmos, infinity often emerges, but it creates problems. The Big Bang. At the very first instant, density, and temperature become infinite in our equations. But this likely signals that our math breaks down, not that reality is truly infinite at a single point. Black holes. At the center, space-time curvature becomes infinite. Another singularity, cosmology. If the universe is infinite in size, then there may be infinite galaxies, infinite Earths, even infinite versions of you. But if infinity exists in physics, it raises deep paradoxes. For example, if there are infinite planets, then every possible history not only exists, but repeats endlessly. Somewhere, there is another you listening to this story. Somewhere else, an infinity of versions of you will never hear it. Our brains are finite. Infinity is not. This mismatch explains why infinity feels so slippery. Try to imagine an infinite beach. Your mind might stretch a coastline longer and longer, but eventually you hit exhaustion. Infinity cannot be fully pictured, can only be reasoned. This is why mathematicians rely on symbols and equations. They do not try to see infinity. They work with it indirectly, like blind sculptors shaping something too large to fit in the room. But even if we cannot imagine infinity, we feel its weight. Infinity appears in our dreams of immortality, our stories of endless afterlives, our fear of unending emptiness, and our hope that something goes on forever. Ironically, the greatest lesson of infinity is about limits. Infinity teaches us that some questions may never close, some paths never finish. In mathematics, infinity allows us to define the infinite series, the calculus of motion, the structure of number systems. In physics, infinity warns us where our theories break. And in philosophy, infinity reminds us that the human quest for knowledge may itself be endless. So, does space end? Mathematics tells us this. Space may be finite, or it may be infinite, but either way, our minds will always find another horizon to chase. Infinity is not just a number. It is the shape of our curiosity. Hilbert's Hotel, Zeno's paradoxes, Cantor's infinities, these are not just games of the mind. They're clues, hints that the universe itself may play by rules beyond our comprehension. And whether or not space ends, one thing is certain. Our imagination never will. Infinity is not only in the cosmos. It is inside us, woven into the very way we wonder, the way we dream, the way we refuse to stop asking questions. And so, the mathematics of infinity is more than numbers. It is a mirror, reflecting our endless journey to understand the infinite sky. When we stare into the night sky, we are not only gazing outward, we are also staring at the limits of our own minds. The question, does space end, is not just scientific. It is philosophical, metaphysical, even spiritual. Because if space does end, if there is an edge, then something must lie beyond. And that something forces us to confront the most difficult idea of all, nothingness. What does it mean for there to be nothing? Not empty space, not darkness, not even a vacuum. True nothingness. Tonight, let us journey into this paradox, the philosophy of boundaries. Imagine, for a moment, that the universe is finite. You travel outward, past every star, past every galaxy, past the last wisp of gas in intergalactic space, till suddenly you reach the edge. What happens next? Do you hit a wall? You step into another universe? Or do you encounter something our minds cannot conceive? Philosophers and scientists have long debated this. Some argue that space cannot have an edge, because an edge requires a beyond, and if there is a beyond, then space continues. Others suggest that space could be finite, but unbounded, like the surface of a sphere. You could travel forever without ever hitting an edge, yet the total extent is still limited. And some believe there really may be a cosmic boundary, a place where the fabric of space-time itself ends, and beyond which there is nothing. But nothing here does not mean empty space. It means no space at all. What is nothing? In everyday language, we think of nothing as an empty room or the black void between stars. But those are still something. Empty space, filled with dimensions, with the possibility of movement. With the laws of physics, true nothingness is different. True nothingness is the absence of all existence. No space, no time, no matter, no laws, no possibility. But here's the paradox. The human mind cannot imagine true nothingness. Try it now. Try to picture nothing. Immediately, your mind fills the blank with darkness, or a black void, or an empty field. But those are still something. This failure reveals something profound. Maybe nothingness is not just unimaginable. Maybe it is impossible. Perhaps existence itself is fundamental, and non-existence is only an illusion of language. The idea of boundaries and what lies beyond has fascinated religions for thousands of years. In Christianity, the universe is often seen as created from nothing, creatio ex nihilo. Here, nothingness is the backdrop against which God speaks existence into being. In Hindu philosophy, the cosmos is eternal, cycling endlessly through creation and destruction. Boundaries are not walls, but transitions. The universe dies only to be reborn. In Islamic thought, the universe has a clear beginning, created by Allah's will. Beyond the physical lies the unseen realms inaccessible to human perception, where angels, souls, and divine realities dwell. In Buddhism, emptiness, unyet, is not nothingness, but a deeper truth. All things lack permanent essence. The boundary of space may reflect the boundary of our illusions. In each tradition, the edge of space is never truly empty. It is filled with divine presence, with metaphysical structure, or with the cycle of existence itself. This suggests something radical. Perhaps the human refusal to accept absolute nothingness is not a weakness, but a clue. Maybe reality itself cannot tolerate nothing. The greatest thinkers have wrestled with this boundary. Parmenides, the Greek philosopher, argued that nothing cannot exist. To think about nothing is already to make it something. Therefore, being must be eternal and unbroken. Aristotle agreed. Nature abhors a vacuum. In his cosmology, there could be no true empty space. Everything must be filled. Descartes wondered about the extension of space. If space is something, then beyond space there must be something else, perhaps another dimension. Martin Heidegger in the 20th century asked the haunting question, why is there something rather than nothing? He suggested that nothingness is not the absence of being, but the background against which being shines. The edge of the universe, then, is not just a physical boundary. It is a mirror reflecting the oldest puzzle of philosophy. Why existence exists at all? Even physics cannot avoid this philosophical question. In quantum mechanics, the vacuum is never truly empty. Even in nothing, particles flicker into and out of existence, driven by uncertainty. What we call nothing is a boiling sea of possibility. Some theories suggest the universe itself may have emerged from nothing, a quantum fluctuation in a vacuum, where time and space spontaneously appeared. But notice, even here, nothing is not really nothing. It is a quantum state, a background with rules, a structure. Science may never touch true nothingness, because even the absence of matter still rests on the stage of space and time. And if that stage ends, then there may be no science left to describe it. There is also a psychological dimension. Humans fear boundaries, because boundaries mean limits. To imagine that space ends is to confront our own fragility. A finite cosmos feels like a box, and boxes feel like cages. At the same time, an infinite universe terrifies us in another way. Infinity is overwhelming, incomprehensible, and unending. So whether space is finite or infinite, both possibilities push us into the abyss of thought. Our fear of nothingness may be less about physics and more about our own struggle with mortality, with meaning, and with the possibility that our lives end just as space might. Even if space has no physical edge, boundaries exist as metaphors. The boundary between knowledge and ignorance, the boundary between life and death, the boundary between the seen and the unseen. When we ask what lies beyond space, we are also asking what lies beyond us. Perhaps the universe's greatest secret is that boundaries are not walls, but doors. And the door beyond space may open not onto nothingness, but onto a realm of reality we cannot yet conceive. So, does space end? If it does, then we face the mystery of what lies beyond. Is it another cosmos, a divine realm, or is it nothing at all? But perhaps the answer is this. Even if there is an edge, our journey never truly stops there. The human mind will always ask, always imagine, always press against the boundaries of thought. The philosophy of boundaries teaches us that the question itself is endless, because every edge we reach, whether in science and religion or in imagination, becomes the horizon of a new world beyond. And maybe that is the true infinity, not the size of the cosmos, but the endless depth of human wonder. For thousands of years, human beings have stared at the night sky and asked, where does it end? We built myths, we built telescopes, and we built equations to stretch our vision outward. But all of those are still just beginnings. The truth is, our exploration of the cosmos has only just begun. And the question of whether space ends or goes on forever may one day be answered not by philosophy, but by technology, science, and human ambition. Let us journey forward in time into the future of exploration. The universe is vast beyond comprehension. Light, the fastest thing in existence, takes more than 46 billion years to reach the edge of the observable universe.
So how far can we fragile humans bound to rockets and fuel really go?
Our farthest physical emissary today is Voyager 1, launched in 1977, after nearly half a century.
It has only just reached interstellar space, a mere 0.002 light-years away.
To reach the nearest star system, Alpha Centauri, would take Voyager more than 70,000 years. With our current chemical rockets, even traveling beyond our solar system is a task that spans lifetimes and civilizations. But human creativity does not accept limits easily. Scientists are dreaming of new methods of propulsion, nuclear fusion drives, using the same reactions that power stars to push ships across interstellar space, solar sails, giant reflective sheets that ride on beams of light pushed by the pressure of photons, antimatter engines, annihilating matter and antimatter for the ultimate burst of energy. And perhaps most daring of all, the concept of warp drives, bending the fabric of space-time itself to leap across unimaginable distances. Even with these advancements, reaching the edge of the universe is another story. The universe is not static. It is expanding faster than we can chase it. In fact, most galaxies are racing away from us so quickly that their light will never reach us. They are already beyond a cosmic horizon we cannot cross. Perhaps humanity will never touch the true edge of space physically, but we may explore it in another way. Through our tools of vision, our bodies cannot travel to the edge. Our minds and our machines might. The James Webb Space Telescope JWST has already given us a new window into the ancient universe, peering back over 13 billion years. But this is only the beginning. Future telescopes will be even more powerful. The Extremely Large Telescope ELT in Chile will have a mirror 39 meters wide, capable of seeing exoplanets in incredible detail. The 30-meter telescope TMT in Hawaii and the giant Magellan Telescope GMT will open windows into the faintest galaxies at the edges of the observable universe. Space-based observatories like LOVOIR or HABEX, planned successors to Webb, may one day detect biosignatures, hints of alien life, light years away. But it is not just telescopes. Artificial intelligence AI is rapidly transforming exploration. AI can sift through billions of signals from the cosmos, spotting patterns humans would miss, can simulate universes, test theories, and optimize telescope observations. One day, AI may even be our guide in interstellar missions, making decisions in real time when humans cannot respond fast enough. With AI as our co-explorer, we may see deeper into the universe than any human mind could manage alone. This is the ultimate question. With all our telescopes, spacecraft, and intelligence, will we ever know if space ends? The first challenge is physical. We cannot see beyond the cosmic microwave background, the afterglow of the Big Bang. Beyond that veil lies the unobservable universe. No telescope can pierce it. But science often works through indirect evidence. By measuring the expansion of galaxies, we infer the universe's geometry. By studying cosmic background radiation, we trace the shape and curvature of space. By modeling inflation and quantum physics, we speculate whether our universe is finite, infinite, or part of a multiverse. Even if we cannot see the end directly, future experiments may hint at it. Subtle patterns in the microwave background could suggest that the universe wraps around like a sphere. High-energy particle collisions might reveal extra dimensions, suggesting boundaries beyond our perception. If we ever detect cosmic bruises, signatures of collisions with other universes, it might mean our space does, in fact, have an edge where it meets another cosmos. But perhaps the greatest exploration is not technological, but philosophical. Human beings are unique because we ask questions beyond survival. We build ships not only to cross oceans, but to test the horizon of reality itself. Whether or not we ever touch the end of space, the act of searching transforms us. It unites us as a species. It expands the boundaries of imagination. It forces us to confront the deepest mystery: why we exist in this universe at all. In this way, even if the end of space remains forever hidden, the search for it gives meaning to our journey. So, does space end? Perhaps we will never know for certain. But the story of humanity is not just about reaching answers. It is about reaching further. Every telescope we build, every ship we launch, every AI we train to scan the stars. These are not just tools. They're extensions of human curiosity, stretching the horizon of knowledge ever outward. One day, perhaps millions of years from now, our descendants may look back and laugh at our limits, just as we smile at the sailors who once feared the Earth's edge. Until then, the future of exploration reminds us of a profound truth. The edge of space may be unreachable, but the edge of imagination is always just one step further. Before we end this exploration, I want you to do something simple. Close your eyes, take a deep breath, and imagine that you are no longer sitting in your room or lying in your bed. Imagine that you are leaving Earth behind. It's not in a rocket, not in a spacecraft, but in the theater of your own mind. This is not science fiction. This is a mind experiment, a way to feel, in the deepest sense, what it means to ask: does space end? So, let us begin this final journey together. You rise above the planet. The blue oceans shrink, the white clouds curl, and the continents fade into a spinning marble. From here, Earth is no longer your home. It is a memory. You move past the moon, where Apollo astronauts once left footprints in dust that has not moved for billions of years. You glide past Mars, its rusty deserts stretching endlessly, and then past Jupiter with storms bigger than Earth itself. One by one, the planets shrink until the sun. Our mighty star is just a small golden coin in a vast black ocean. Already you feel the mystery growing. For every step outward, there are thousands more ahead. Now imagine continuing outward. You soar through the asteroid belt, silent ruins of a world that never formed. You skim past comets, frozen travelers carrying ancient water and dust. And then you rise above the plane of the Milky Way itself. From here, our galaxy is no longer billions of stars around you. It is one shining spiral, a pinwheel glowing against the abyss. You are no longer bound to human scales. Light and distance stretch. Light years pass in the blink of an eye. But the Milky Way is just one island. All around it, countless other galaxies shine, each with billions of stars, billions of planets, billions of mysteries. And still, you continue. At last, after a journey beyond imagination, you approach the cosmic horizon, the farthest light that has ever reached us. You see the cosmic microwave background, a faint whisper of the universe's birth, a glow left behind when the first atoms formed. Beyond this, your eyes cannot see. No telescope can. But in this mind experiment, you press further. You cross that invisible line, and suddenly, you are in the unknown. Here, imagination takes over where science stops. Perhaps beyond the horizon, the universe continues forever, galaxies without end, stretching into infinite night. Or perhaps it curls back on itself like the surface of a sphere, looping endlessly so that traveling forward eventually brings you back to where you began. Or maybe the boldest possibility: you cross into another reality entirely, another universe, with different laws of physics, strange colors, alien patterns of stars. In this place, there is no certainty, only mystery. And that mystery is the true edge of space. Not a wall, not a boundary, but the endless question: what lies beyond what we can know? Now, pause. Imagine yourself floating in this infinity. Your body is gone. Your mind is light itself. There is no up, no down, no distance, no time, only the vast silence of the cosmos. And in that silence, you realize something profound. The edge of space is not a place. It is an idea. A reflection of human curiosity projected outward into the night. Every time we ask if space ends, we are really asking about ourselves, about the boundaries of our knowledge, about the limits of our imagination, about the shape of existence itself. And maybe, just maybe, the real answer is that there is no end, because curiosity itself is infinite. Slowly, gently, let yourself return. The galaxies blur, the Milky Way shrinks, the sun grows brighter, and Earth spins into view once again. You descend through the blue sky, through the thin veil of atmosphere, and return to the ground. You are back in your room, back in your bed, back where you began, but you are not the same. Because for a moment, you touched infinity. So, does space end? You may never know. Science may forever meet a horizon it cannot cross. Telescopes may reach their limit. Rockets may fall short. Equations may whisper but never shout the truth. But perhaps that is not a failure. Perhaps it is the greatest gift the universe has given us. An endless horizon to dream toward. Because in the end, the edge of space is not a line to be crossed. It is a fire that keeps burning. A question that keeps asking. A mystery that keeps humanity reaching further. And as long as we keep asking, we will never stop exploring.